Radiographic exposure technique. This is chapter 11 from the Johnston and Faber book, Essentials of Radiographic Physics and Imaging. As a radiographer, you know that we are responsible for selecting the exposure factors to produce a quality image. We need to have knowledge of how these factors affect the image. And then also we need to know about radiation protection. So we need to know about exposing patients to the least amount of radiation necessary to produce a diagnostic quality radiograph. And that is where a LARA will play, as low as reasonably achievable. So we want to give patients the least amount of radiation, but we need to give the image the enough radiation to be able to give us a diagnostic quality radiograph. The quantity of radiation reaching the patient affects the amount of remnant radiation reaching the IR. The product of milliamperage and exposure time has a direct proportional relationship with the quantity of X-rays produced. And we know that milliamperage times seconds gives us our mass. Once the anatomic part is adequately penetrated, as the quantity of X-rays is increased, the exposure to the IR proportionally increases. Conversely, when the quantity of X-rays is decreased, the exposure to the IR decreases. Therefore, exposure to the IR can be increased or decreased by adjusting your mass, which is the amount of the radiation. Because the mass is the product of milliamperage and exposure time, increasing milliamperage or time has the same effect on the radiation exposure. So shown in figure 11-2 here, mass and radiation exposure, it's showing that as the quantity of X-rays is increased, the exposure to the image receptor proportionally increases. So it is directly proportional. So we can see on the left, there is less mass, and then also there is less exit radiation reaching the image receptor. On the right, we have more mass, which means more exit radiation reaching the image receptor. Primary factors, milliamperage and exposure time. So your exposure time is the seconds. It is directly proportional to radiation quantity, directly related to the IR exposure, and inversely related to MA to maintain the IR exposure. We have the formula MA times time, which is your seconds, equals mass. And you always have the lowercase m, the uppercase A, and the lowercase s. Many variables can affect the amount of mass needed to produce a diagnostic image. It could be the patient's age, condition, or the presence of a pathologic condition, and those all could affect the amount of mass required for the procedure. If the mass is too low, low exposure to the digital IR, image brightness is adjusted during computer processing to achieve the desired level. The level of brightness has been adjusted. There may be increased quantum noise visible within the image if that's the case. And if the mass selected is too high, which is a high exposure to the digital IR, the brightness can also be adjusted, but the patient has received more radiation than necessary with that. The radiographer should be diligent in monitoring the EI, which is your exposure indicator. Those values they need to monitor to ensure that quality images are obtained with the lowest possible dose to the patient. If the mass is too low, which is low exposure to the digital IR, image brightness is adjusted during computer processing. although there may be increased quantum noise visible within the image as well. So the radiographer should be diligent in monitoring the EI values to ensure that quality images are obtained with the lowest possible radiation dose to the patient. A radiographic image repeated because of insufficient or excessive exposure generally requires a change in mass by a factor of at least 2. So you want to basically decrease your mass in half. So if you look at the image here, this image is showing quantum noise. With A, this is a quality image created using sufficient mass. And then in image B, this is an image created using insufficient mass and results in increased quantum noise visible within the image. You can see more bony detail in image A, and in image B, it's really grainy. You have a lot of noise, so you have less anatomic detail to the bony structures. If the mass selected is too high, high exposure to the digital IR, the brightness can also be adjusted, but the patient will have received more radiation than necessary. The radiographer should be diligent in monitoring the EI values again to ensure that quality images are obtained with the lowest possible radiation dose to the patient. A radiographic image repeated because of insufficient or excessive exposure generally requires a change in mass by a factor of at least 2. So again, we would be decreasing it by half or increasing it, doubling it. So in this figure here, we're looking at exposure errors and image brightness. Exposure errors can be computer adjusted to maintain the image brightness. So in A, the image is created with sufficient mass. In B, the image is created with insufficient mass and results in increased quantum noise. And then C, the image is created with excessive mass and results in decreased quantum noise visible. Kilovoltage, kVp, alters the amount and penetrating ability of the X-ray beam. kVp affects the amount of radiation exposure to the IR. So looking at this figure here, this is kVp and radiation exposure. Increasing the kVp increases the penetrating power of the radiation, and it also increases the exposure to the image receptor. So if we look at here, we have low energy kVp beam, so we have less kVp going through the patient. Most of the X-ray photons are absorbed by the patient, and few are going to strike the IR. Over here to the right, we have high energy kVp beam, so we're sending more kilovoltage towards the patient. And then we have photons that have more energy to penetrate the part, so less is absorbed and more hit the IR. This diagram here is showing the change in kilovoltage peak. 2 emission spectra illustrating the result of an increase in kVp, which is the purple curve. The green curve is where the kVp started at 72 kVp, and then the peak went up to 82. Increases in kVp increase the quantity and quality of radiation. The keV is the kilo electron volt, and the kVp is the kilovoltage peak. So this line here would be the keV, and it's showing you the difference. When we have 82 kVp, we will have, let's see, about 80 keV. And when we have 72 kVp, we will have about 73, let's say, keV. When the kVp is increased at the control panel, a larger potential difference occurs in the X-ray tube, giving more electrons the kinetic energy to produce X-rays and increasing the kinetic energy overall. The result is more photons, which is the quantity, and higher energy photons, which is the quality. Increasing or decreasing the kVp changes the amount of radiation exposure to the IR and the subject contrast produced within the image. The effect of kVp on the digital image is similar to the effect of mass. If we have too much radiation reaching the IR, this produces a digital image with the appropriate level of brightness as a result of computer adjustment during image processing, but it will overexpose the patient. If you have too little radiation reaching the IR, this produces a digital image with the appropriate level of brightness, but the increased noise decreases the image quality. So in this image here, we're looking at changes in kVp and image quality dependent on the technique that we set. So with image A, this image is produced using 70 kVp at 2 mass. Image B is using 50 kVp at 2 mass, and this results in higher subject contrast and computer adjusted to maintain brightness. However, the increased quantum noise is visible with image B. In image C, this image was produced using 93 kVp at 2 mass and results in lower subject contrast, and the computer adjusted it to maintain brightness. However, the patient exposure is increased for image C. Assuming that the anatomic part is adequately penetrated, changing the kVp does not affect the brightness of the digital image. Image brightness is going to be controlled by the computer processing. Kilovoltage is not typically manipulated to vary the amount of IR exposure because it also affects contrast. The 15% rule is we are changing the kVp by 15%. It would be the same effect as doubling the mass or reducing the mass by 50%. To maintain exposure to the IR, when the kVp is adjusted by 15%, either up or down, the mass needs to be changed by a factor of 2. So you're either going to decrease it by 2 or increase it by 2. The 15% rule. So a 15% increase in kVp has the same effect as doubling the mass. A 15% decrease in kVp has the same effect as decreasing the mass by half. Increasing the kVp by 15% increases the exposure to the IR unless the mass is decreased. Also, decreasing the kVp by 15% decreases the exposure to the IR unless the mass is increased. So it's very important to always do both. You have to, if you increase kVp, you're going to do what? You need to decrease your mass. If you're going to decrease kVp, you need to increase your mass. So we want to increase the exposure to the IR. We want to multiply the kVp by 1.15, or you can just take the original kVp and add 15%. So we have 80 kVp, which is our original kVp. We want to increase the exposure to the IR, so we will add 15%. So 80 plus 15% would be 92 kVp. To decrease exposure to the IR, multiply the kVp by 0.85, or you can just take the original kVp, which is 80, and subtract 15%, which will give you 68 kVp. And remember to maintain exposure to the IR. When increasing the kVp by 15%, we want to divide the original mass by 2. So you're going to cut it in half. And then when decreasing the kVp by 15%, you want to multiply the mass by 2. Higher kVp increases the penetrating power of the X-ray beam and results in less absorption and more transmission in the anatomic tissues, which results in less variation in the X-ray intensities exiting the patient and hitting the IR. As a result, images with lower contrast are produced. When a low kVp is used, the X-ray beam penetration is decreased, resulting in more absorption because now it has more time, it's going slower, and less transmission, which results in greater variation in the X-ray intensities exiting the patient. And this produces a high contrast radiographic image. So if you look at the top image here, you have high kVp, and it's going through bone, fat, and air. And because it is a higher kVp, the penetrating power is higher, so it has less time to be absorbed by the bone, fat, and air because it's pushing through fast. And then you will have more interaction with the IR. The bottom image, you have a low kVp, so it's going in slower. It has more time now to be absorbed by the bone, fat, and air because it's not penetrating all the way through, it's going in slow. And so because of the absorption, now you have less exposure interacting with the IR. For most anatomic regions, an accepted range of kVp provides an appropriate level of radiographic contrast. As long as the kVp selected is sufficient to penetrate the anatomic part, the contrast can be adjusted by the computer to display the desired contrast for the anatomic region. And that's what we do with post-processing. Many secondary factors affect the radiation reaching the IR and image quality. It is important for you as the radiographer to understand their effects individually and in combination. And we will be talking about all of these different secondary factors: the focal spot size, the SID, the OID, central ray alignment, grids, beam restriction, generator output, tube filtration, compensating filters, and then patient factors such as size of your patient, any pathologies, age of your patient. On the control panel, the radiographer can select whether to use a small or a large focal spot size. When the radiographer selects a particular focal spot size, they are actually selecting a filament size that is energized during X-ray production. Shown in this figure here, the focal spot size influences the amount of unsharpness recorded in the image. As focal spot size changes, so does the amount of unsharpness. In image A, it's a larger focal spot, and in image B, a smaller focal spot. The physical dimensions of the focal spot on the anode target in X-ray tubes range from 0.5 to 1.2 millimeters. Small focal spot sizes are usually 0.5 or 0.6 millimeters, and then large focal spot sizes are 1 or 1.2 millimeters. Focal spot size is determined by the filament size. The distance between the source of the radiation and the IR, source to image receptor distance, is the SID, and it affects the amount of radiation reaching the patient. Because of the divergence of the X-ray beam, the intensity of the radiation varies at different distances. Looking at the image here, SID and radiation intensity, beam intensity varies as a function of the square of the distance. So looking at A, this decreases the overall intensity of the X-ray beam reaching the IR, and B, as the SID is increased, the X-ray intensity is spread over a larger area. The relationship between distance and X-ray beam intensity is described by the inverse square law. So the inverse square law states that the intensity of the X-ray beam is inversely proportional to the square of the distance from the source. Because beam intensity varies as a function of the square of the distance, SID affects the quantity of radiation reaching the IR. So as SID is increased, the X-ray intensity is spread over that larger area. So this decreases the overall intensity of the X-ray beam reaching the IR. Because increasing the SID decreases X-ray beam intensity, the mass must be increased accordingly to maintain the proper exposure to the IR. When the SID is decreased, the beam intensity increases. Therefore, the mass must be decreased accordingly to maintain proper exposure to the IR and to prevent burnout. Shown is the mathematical equation for the direct square law, or the exposure maintenance formula. So you have mass 1, which is your original mass, divided by mass 2, which is our new mass, equals SID1, your original SID, squared, divided by SID2, which is your new SID, squared. And then that will give you your adjustment in mass and what your new mass needs to be. So you will be solving for mass 2. So we know our old SID, or our original SID. We know our new SID, and we knew the original mass. So when you do this formula, this will give you your new mass, and what with this new SID, what your mass needs to change to. Certain circumstances, such as trauma or mobile radiography, do not allow for standard distances to be used because sometimes the rooms are very small. In these circumstances, the radiographer must determine the change needed in the mass to obtain a quality radiograph. When a 72-inch SID cannot be used, adjusting the SID to 56 inches requires half the mass. When a 40-inch SID cannot be used, adjusting the SID to 56 inches requires twice the mass. So this quick method of calculating mass changes should produce the sufficient exposure to the IR. So shown in this figure here, it's SID and size distortion. So a long SID creates less magnification than a short SID. So you can see that in figure A, we have a very short SID, and it's going to create magnification, so it'll create a larger size. And then in figure B, we have a very long SID, so it will decrease the magnification and give us more of a true size of the anatomy. So it's very important for chest x-rays. We always do chest x-rays at 72 inches, and that is because we are trying to decrease the magnification of the heart. When distance is created between the object radiographed and the exit radiation continues to diverge, less overall intensity of the X-ray beam reaches the IR. So shown in this figure here, this is OID and air gap. So distance created between the object and the image receptor reduces the amount of scatter radiation reaching the image receptor. So you always want to have the least amount of OID possible. OID affects the following. It affects radiation intensity reaching the image receptor. It also affects the amount of scatter radiation reaching the image receptor. It affects magnification and spatial resolution. So whenever the amount of scatter radiation reaching the IR is reduced, the radiographic contrast is increased. The amount of OID required to increase contrast depends on the percentage of the scatter exiting the patient. And then for anatomic areas that produce a high percentage of scatter, less OID is needed to increase the contrast for that anatomic area that produces less scatter. When distance is created between the area of interest and the IR, the diverging exit beam records the anatomic part with increased size distortion or magnification. So shown in this figure here, we are looking at OID and size distortion. A long OID creates more magnification than a short OID. So if we're looking at A, the image A is larger than that in B because the object is farther from the image receptor. So you can see there in image A, you can see the X-ray tube, the X-ray beam coming down, and then you have a ton of OID from the object to the image receptor. There's a big space there. So now you can see how magnified that bone is on the image. And then when we're looking at B, you can see the X-ray tube. You can see the object is closer to the image receptor. So now it looks true to size, or just a little bit larger than true to size, but it has definitely decreased the magnification of the image, or of the bone. The magnification factor, or MF, indicates how much size distortion or magnification is demonstrated on the radiograph. Source to object distance is the SOD. This is the distance from the X-ray source, which is the focal spot, to the object being radiographed. SOD can be expressed mathematically. So to find out our magnification factor, we have to do SID over SOD. So SID divided by SOD. So you'll take the SID and you'll divide it by the source to object distance, and then this will give you your magnification factor. Shape distortion of the anatomic area of interest can occur from inaccurate CR alignment of the tube, the part being radiographed, or the IR. So if the central ray alignment of the tube or the part or the IR is in any way inaccurate, it can cause all kinds of different distortions. Any misalignment of the CR among these three factors alters the shape of the part recorded on the image. So we're looking here at A. A is a proper alignment among the X-ray tube, part, and image receptor. So A is what you want. B is improper alignment among the X-ray tube, part, and image receptor. The illustration on the left of B shows the image receptor is misaligned to the part, and the one on the right of B shows the part not parallel to the image receptor. You can see the improper alignment of the radial head with the capitulum in the image. And then in C, we have improper alignment among the X-ray tube, part, and image receptor. So image C has shape distortion, and this is because of the central ray is not perpendicular to the part, and there's elongation of the olecranon process in the image. The effect of less scatter or unwanted exposure on the image is to increase the radiographic contrast. So grids are typically used only when the anatomic part is greater than or 10 centimeters or greater in thickness, and more than 60 kVp is needed for that exam. The more efficient a grid is in absorbing scatter, the greater its effect on the radiographic contrast. Grids also absorb some of the transmitted radiation exiting the patient and therefore reduce the amount of radiation reaching the IR. So we can see in this image here, it's grids and scatter radiation, scattered absorption. So most of the scatter radiation toward the image receptor is absorbed when a grid is used. So if you're looking at the primary X-ray beam, it's going through the patient and most of it is being absorbed. Scatter radiation hits the lead strip and is absorbed by the grid, and then just your useful beam is hitting the image receptor. When grids are used, the mask must be adjusted to maintain the exposure to the IR. The more efficient a grid is in absorbing scatter, the greater the increase in mass. The grid conversion formula is a mathematical formula for adjusting the mass for changes in the type of grid. So we have that grid conversion formula over in the chart there. You can see it's mass 1 over mass 2 equals grid ratio 1 over grid ratio 2. When a grid is added, the radiographer must use the correct grid conversion factor to multiply by the mass to compensate for the decrease in exposure. When a grid is removed, the correct conversion grid factor must be divided into the mass to compensate for the increase in exposure. So here's a mathematical problem using the grid conversion formula. So we have a quality image that's obtained using 2 masks at 70 kVp. And this is without using a grid. So no grid, the grid conversion factor for that would be 1. So you would set up your formula. You would have 2 masks as mass 1. And then we're solving for mass 2. And then for the grid ratio 1, we would have 1 because we were not using a grid. But now we're looking for our new mass because we're going to add a 12-to-1 grid. So then we look there, 12-to-1 grid is 5. So our grid ratio 2 would be 5. So again, we have mass 1 is 2. Our grid ratio 1 is 1 because it's no grid. Our grid ratio 2 is 5 because we're changing it to a 12-to-1 grid ratio. And then we're solving for mass 2. So you do 2 mass times 5. You're just cross multiplying. And then that equals 1. And then 1x. And then we're doing 10 mass equals x. So you're just doing 2 times 5. And that is 10 mass. A quality image created without a grid is seen in image A. Image B is an image created with a grid, but no adjustment in mass. And then because of that, it has a higher contrast, but increased quantum noise visible. And then image C is created with a grid and appropriate mass adjustment. So image C has a higher contrast than image A and less noise than image B. So your ideal image would be image C. Any change in the size of the X-ray field alters the amount of tissue irradiated. Beam restriction is very important for patient protection from radiation. A larger field size increases the amount of tissue irradiated, causing more scatter radiation to be produced. It also increases the amount of radiation reaching the image receptor, which results in less radiographic contrast. If we are collimating and we are using beam restriction, we should have a smaller field size. And this will reduce the amount of tissue that's irradiated, and it will reduce the amount of scatter radiation produced. It also reduces the amount of radiation reaching the IR, and this is going to result in higher radiographic contrast. So it's very important to always collimate. The effect of collimation is greater when imaging large anatomic areas, performing exams without a grid, and using a high KVP. Looking at the figure here for generator output, there are 3 emission spectra illustrated in the result of a change in the generator type. So we have high frequency, we have 3-phase, and we have single phase. As the efficiency of the generator type increases, so does the X-ray quantity given the same amount of electricity used, the KeV and the KVP. But we're looking at the kilo electron volt. So generators with more efficient output require lower exposure technique to produce an image, and then generators must be calibrated periodically to ensure that they are producing consistent radiation output. Small variations in the amount of tube filtration should not have any effect on radiographic quality. X-ray tubes that have excessive or insufficient filtration may begin to affect image quality. The increased X-ray energy, KVP, and the scatter production decrease radiographic contrast. We can see here in this image here, you can see 2 emission spectra. One is 2 millimeters of aluminum added filtration, and one is 4 millimeters of aluminum added filtration. So you can see the added filtration is the green curve. Increases in filtration are going to decrease the quantity and increase the quality of radiation. AL is aluminum, and KeV again is kilo electron volt. X-ray tubes that are operated above 70 kVp are required to have a minimum of 2.5 millimeters of aluminum filtration. The amount of increase in the mass depends on the thickness and the type of compensating filter. Additionally, the use of a compensating filter increases the exposure to the patient. When imaging in an anatomic area that varies greatly in tissue thickness, a compensating filter can be placed in the primary beam to produce a more uniform exposure to the image receptor. The use of compensating filters requires an increase in mass to maintain the overall exposure to the receptor. Compensating filters are not typically used in routine radiography today, but always remember if you're using a wedge filter, this would be for the toes primarily, because when we're doing a foot x-ray, the middle of the foot is a lot thicker than the toes. So the KVP and the mass that we have going through the foot tends to burn out the toes because the toes are so thin. So we'll use a wedge filter, and the thicker part of the wedge filter goes over the toes. So thick over thin. So the thick wedge filter goes over the toes, and then the thinner part of the wedge goes over the foot. And then it'll give us more of a uniform exposure to the foot and not burn out the toes. Body habitus refers to the general form or build of the body, including size. The sthenic body habitus accounts for approximately 50% of the adult population and is commonly called a normal or average build, and that is the image in the top right. Hyposthenic accounts for approximately 35% of adults and refers to a similar type of body habitus as sthenic, but with a tendency toward a more slender and taller build. These two types of body habitus combined account for about 85% of adults, and hyposthenic is top left. Hypersthenic and asthenic body habitus types are more extreme and are less common. The hypersthenic is a large, stocky build and accounts for about 5% of adults, and asthenic refers to very slender body habitus and is about 10% of adults, and asthenic is bottom right. Maintaining the exposure to the IR when imaging a thicker part requires the mass to be increased accordingly. In addition, when a thinner anatomic part is being radiographed, the mass must be decreased. Because X-rays are attenuated, a general guideline is that for every change in part thickness of 4 to 5 centimeters, the radiographer should adjust the mass by a factor of 2. So here you can see in this figure here, it's showing tissue beam attenuation. X-rays are attenuated and generally reduced by approximately 50% for each 4 to 5 centimeters of tissue thickness. So you can see there's 100 X-rays coming in. It's decreased to 50 and then decreased to 25 because of the tissue. Brightness can be computer adjusted when the mass is not properly altered for changes in part thickness. However, increased quantum noise or unnecessary patient exposure can be the result of that. If you look at image A, that is a quality image. Image B was created with added thickness but no mass adjustment, which resulted in increased quantum noise visible. And then image C is created with added patient thickness and appropriate mass adjustment, which results in decreased quantum noise visible. Anatomic structures that have a wide range of tissue composition demonstrate high subject contrast. Anatomic structures that consist of similar type tissue demonstrate low subject contrast. So anatomic structures do affect contrast. Changing the KVP alters its absorption and transmission with anatomic tissues. If you look at the figures over here, the figure to the left is a high subject contrast tissue. Higher contrast resulting from greater differences in the radiation absorption for tissues that have greater variation in composition. And then the figure to the right is low subject contrast tissue. Lower contrast resulting from fewer differences in the radiation absorption for tissues that are more similarly composed. Radiation protection. So for good radiation protection, we want to use a higher kV and a lower mass. We want to limit the X-ray field size to just beyond the anatomic area of interest, so we want to use beam restriction. We want to minimize grid use and use a lower ratio. And we want to carefully select the digital exposure techniques because excessive radiation exposure and digital imaging kind of go hand in hand. So this chart here provides exposure factors and their effect on the primary and exit X-ray beam. So if we're looking at mass, increasing the mass is going to increase quantity of the beam reaching the patient, but also the exit beam reaching the image receptor. It's going to increase the quantity of both. Decreasing the mass will decrease the quantity of the primary beam reaching the patient and the quantity of the exit beam reaching the IR. Increasing KVP. This will increase quantity and quality of the beam reaching the patient. It's going to also increase quantity and quality of the beam reaching the IR. Decreasing KVP, again, will decrease the quantity and quality of the beam reaching the patient and decrease quantity and quality of the beam reaching the image receptor. If you have a smaller focal spot size, It has no effect on the primary beam reaching the patient or the exit beam reaching the image receptor, no matter if it's a smaller focal spot size or a larger focal spot size, it has no effect. SID, increasing your SID is going to decrease the quantity of the beam reaching the patient and decrease the quantity of the beam reaching the IR. And then for the opposite, if we decrease our SID, it will increase the quantity of the beam going to the patient and the quantity of the beam reaching the IR. For OID, we want to increase our OID. It has no effect at all on the primary beam reaching the patient, either increasing OID or decreasing OID. But if we increase the OID, it will decrease the quantity and scatter of the beam reaching the IR. And if we decrease our OID, it will increase the quantity and scatter of the beam reaching the IR. Your central ray angle, if you increase the angle, it will decrease quantity of both. And for grid, if we increase grid ratio or decrease grid ratio, it has no effects on the primary beam reaching the patient, but it does have effects of the exit beam. So increasing grid ratio decreases the quantity and scatter of the beam reaching the IR. Decreasing grid ratio will increase the quantity and the scatter reaching the IR. Beam restriction, increasing collimation will decrease the quantity of the beam reaching the patient, and it will also decrease the quantity and scatter reaching the IR. Decreasing collimation will increase the quantity of the beam reaching the patient and increase quantity and scatter going to the IR. If you have single phase generator, it will decrease the quantity and quality of both the beam reaching the patient and the IR. If you have a high frequency generator, it will increase quantity and quality of both the patient and the IR. Adding a compensating filter will decrease the quantity of the primary beam reaching the patient and also decrease quantity of the exit beam reaching the IR.